Hello and welcome to a Maths with Harry lesson. In this video, we're going to have a look at stretching graphs. In the previous video, we had a look at translating graphs, and we found that there's two ways to do that. We can translate a graph up and down, or we can translate a graph left and right. So vertical translation or horizontal translation. And that is very similar for when we are stretching graphs. There's two ways to do that, and the two ways are vertical or horizontal. We can stretch something vertically, so stretching it in the vertical direction, or stretching something horizontally by stretching it in the horizontal direction. So we'll write those two things on in green. We've got a vertical stretch, or we've got a horizontal stretch. Now we can either do one of those, or we can actually do two of those things. We can do both of them at the same time. We can do a vertical stretch, do that, and then do a horizontal stretch as well, okay? But in this video, we're just gonna have a look at doing one of each. So, first of all, let's have a look at a vertical stretch. If we've got the graph of y equals a times f of x, so some constant a outside the front, we have a function f of x, we multiply it by a, that is, and I'll write it in red, that is a stretch, and we use the word stretch, of the original graph, which is y is equal to f of x, just the original function, by what we call a scale factor. By a scale factor, a in the vertical direction. So if we have a original graph, y is equal to f of x, and we multiply it by a, some constant, can be positive or negative, it is a stretch by the scale factor of that a in the vertical direction. Let's have a look at an example of this, and I've just taken a picture from the textbook, okay? What we have is, we have this black graph, which is the original graph. We can see that is y is equal to f of x. And we've done two different vertical stretches. We've got this black graph, f of x, and we've got, first of all, the red graph. Let's look at that. The red graph we can see is y is equal to 2 times f of x. If we think about what that actually means first before we think about the graph, well, we've got a function, and we've got a different function which is 2 times f of x. All that is going to do is multiply all of our y values by 2. Because we're kind of doubling the function, okay? So what we're doing is, we're doing a stretch with scale factor 2 in the y direction, the vertical direction, and all that means is the y values are doubled because they're becoming 2 times the function, and then y is 2 times the function. So everything is going to be multiplied by 2 in the y direction. And we can see this was our original function. We kind of have it looking like this now. All of our values are going to be doubled. So we started with a 1 here as our y-intersection. Here, that was our normal function, or our original function. Doubling it means it moved here to be 2, and then everything else doubles. Okay, so it's this red graph here. We can also half it as well, and if you notice, going from black to red, we kind of squished in a little bit. It was a little bit of the stretch inwards, if you like, and it got a little bit thinner, the graph. Here we have y is a half x, so our value of a here is a half. We've got a half of f of x, and that's the blue graph here, okay? It becomes a little bit fatter, if you like, but that's because we're basically stretching it by a half in the y direction, so all our y values half. We're going to come at this point here, if you look, I'll highlight it in yellow. That's now our intersection point on the y-axis, and that intersection point is going to be a half, because we went from being 1 on our original graph. Halving the function means that yellow value will be a half, so it'll be at the point 0, a half, okay? And you notice that all of them cross through at -1, and that's because that is the x-axis intersection. or intersection. And we're not doing anything in the horizontal direction, it's just a vertical stretch, so they're all still going to pass through the x-axis at -1. Okay, so those are different stretches. If we have a integer like 2 here, we can see this is the stretch and it kind of stretches inwards a little bit, and we do a stretch in the horizontal, in the vertical direction, and the blue is a half, so it becomes a little bit fatter, if you like. Okay, so that's just a sort of interpretation on the graph. What happens though if we have the graph of y equals f of a times x? So here we had a times f of x. Here we've got our constant a multiplying just with the x. We're not multiplying the whole function by a, we're just multiplying x by a. Well, in that case, and I'll write it in red again, that is a stretch. We're still doing a stretch, and it's still a stretch of the original graph. So the original graph is just y equals f of x, that function, by the scale factor, and it's a little bit different here. It's not by the scale factor a, it's by the scale factor 1 over a. And it's not in the vertical direction, so up and down, it's in the horizontal direction. So we'll write that on here, in the horizontal direction. So let's have a look at that with an image. Here we have a quadratic. Okay, we can see the black graph again is our original quadratic, and we can see it's quite thin. Okay, it goes up and down here. It's got a y intersection at 4, and it's got an x intersection or a turning point here at 2. Okay, and we've got 2 different horizontal stretches. We can see the blue graph here is y is f of a third of x. What we took here is the reciprocal of our constant. The scale factor is the reciprocal, 1 over that. Okay, if we've got a third, then our scale factor will be 1 over a third, which is 3. Okay, so the scale factor here will be 3. And because it is a stretch in the horizontal direction, all of our x values will be multiplied by our scale factor, which is 3. Okay, so the turning point here was at an x value of 2. That's now going to become 3 times bigger. It's going to now become the turning point at 6. Okay, we can see we have a y intersection at 4, and because that is on the y-axis, x is 0 there, we're doing something to the horizontal. We're not doing anything to the vertical here, because it's a horizontal stretch. That y-intercept is going to stay the same. Okay? And we can see the general shape of the graph. When we multiply it by this third here, we're going to do a scale factor of 3. So everything's going to become quite a bit bigger. We can see we were quite thin here, and then we got quite a bit larger when we did that scale factor of a third. Okay, or scale factor of 3. Okay. And then we had here, well, this is our original graph. The red graph is y is f of 2 of x. So that's going to be a scale factor of a half. And because we're doing a horizontal stretch, everything in the horizontal direction, so all of our x values, will be halved, because our scale factor will be 1 over 2. So it's going to become quite a bit thinner than our original graph. Okay, let's have a look at some examples ourselves. This is example 1, so pause and have a go if you want to. Whenever you're asked a question like this, it's always useful to sketch the original graph first. Just like we did here with the black graph, it's always useful to sketch the original graph and then sketch your stretches. Okay, so we've got a function 9 minus x squared, and we're wanting to sketch the graphs of y is f of 2x and y is 2f of x, when f of x is 9 minus x squared. Okay, let's see whether you've had a go, and hopefully you managed to sketch the quadratic. 9 minus x squared is not that hard to sketch, and I'll sketch it twice. I'll do it on the same axes as I'm doing these two graphs. Okay, so let's start by sketching f of x. I'm going to write that in a different form. I'm going to write f of x with the x squared term first. So it's minus x squared plus 9. Okay, now I'm going to ignore that plus 9 for the minute. Let's just put a cross through that and ignore it. Don't forget about it, but we'll ignore it for the minute. And we'll just sketch the original graph. And to start, I'll do it in red. I'll just sketch minus x squared. That's quite simple to sketch. It looks exactly like, let's just get this right. It looks exactly like that. Okay, that's minus x squared. We've looked at that in previous videos. Then, in the previous video, we looked at how we can translate functions up and down. If I then invite this plus 9, back, all that means is move the minus x squared graph up by 9. Add 9 to every coordinate, basically. So all we're doing is moving that in the vertical direction, or the positive y direction, by 9. So it's going to look something like that, okay? No horizontal change, just a vertical movement up by 9. So I can add some coordinates on here. The turning point will be, well, nothing in the x direction, 9 in the y direction because we moved it up by 9. And then we need to think about, what are those 2 points? Well, those are the roots. Let's work out the roots. 9 minus x squared is equal to 0. So x squared is equal to 9. Then x is equal to plus or minus the square root of 9, which we know is plus or minus 3. Okay, so just working out the roots, set equal to 0. So we know we've got a plus or minus 3 there. So this is going to be plus 3. So 3, 0, and then this will be minus 3. And it's 0 in the y direction because we're on the x-axis. Okay, so that's our original graph. Now what we want to do is sketch the graph of f of 2x. Okay, so our scale factor here, and I'll write this in blue, the scale factor will be 1 over that number. So 1 over 2, which is a half. So if we look here, what we had is we had 2 here, okay, so everything came a lot thinner. Our scale factor will be a half. So we're going to sketch the exact same graph, just a lot thinner, and all of our points in, well, we're with the x here, so we're inside the bracket here with our 2. It's going to be a horizontal stretch, that's the word. Everything's going to become a lot thinner. All of our x values are going to be multiplied by our scale factor. In other words, they're going to half. Okay, so we're going to get something like this, and I'll sketch in blue. We're going to get this. We're still going to pass through the y-axis there because we have a x value of 0, but we're going to get a thinner graph that looks something like that. Okay, it doesn't have to be perfect as long as we put some scaling on to help what the graph looks like. Okay, so again, we're still going to have that same turning point there, but our 2 roots are going to be a little bit different. Okay, they're going to be a half of what they originally were because our scale factor is a half. Okay, so that point there is going to be 3 over 2, 0, and that point there is minus 3 over 2, 0. Okay, so that is what our graph of f of 2x looks like. Okay, it is a horizontal stretch because we are inside the bracket, just like we had up here. A of x, f of a of x is a horizontal direction stretch, so we've got that here. And then our scale factor is 1 over the number in front of x, 1 over 2, which is a half. Everything then becomes sort of stretched a little bit inwards by a half. Okay, everything comes a half of what it was in the x direction. Okay, let's have a look at part B, which is 2 times f of x. So again, I'm going to sketch my original graph. Oops. You don't really have to sketch it, but it's always useful to do that. And I'll add the turning point at 0, 9, and our roots at minus 3, 0, and 3, 0. And this time what we have is our constant, which is 2. We have that outside of our function, so 2 times our function. What that means is we're doing a stretch in the vertical direction by a scale factor of 2. okay? So it's going to look something like this. I'm just going to duplicate this to make it a little bit easier, and I'll make it a different colour. This time we will do it, let's do it in this nice purple, and it's going to look something like this. It's going to be a vertical stretch, so everything on the x-axis is going to stay the same, just like it did up here, okay? On the x-axis, we were doing a vertical stretch here. Everything stayed the same. They all crossed through -1. So they're still going to have the same roots here, but what's going to change is our intersection point, and it's going to kind of stretch. In real life, it would kind of maybe look something like that. It would be double, but I don't have the room on my graph, so we'll put it there. But what I will indicate is that that is the point 0, 18, okay, and hopefully you see why that's 0, 18, because we've got a 2 outside the front here, so all of our y values will be multiplied by 2. Not 1 over 2, that's when we're kind of inside the function. We're outside the function here, so it's going to be a 2, and then the 9 will be multiplied by 2 to give us 18, okay, and it's always just important when you're doing your sketches to give, and they should still cross through the same roots. Let's just zoom in and improve that a little bit to cross through those roots like that. There you go. Okay, this should still cross, still cross through there. This should still sort of put on your intersection point as long as everything looks clear like that. Okay, so now let's have a look at how we can reflect in the y-axis. I've got a function here, x squared minus 2x, and I've got arrows on the function here to indicate it's going to continue forever, okay? It's continuing all the way up there. Let's say we have a look at reflecting that function in the y-axis. What does that actually look like on the graph? Okay, well, the y-axis is actually disguised as the f of x axis here, but it's just another way of writing the y-axis. This is our y-axis, okay? If we reflect that in the y-axis, it's going to look something like that. If you can imagine this as being a mirror line, reflecting just means sort of bringing everything over. It's just going to flip in the y-axis, okay? And again, we could maybe add arrows on here to show that our graph is continuing forever, okay? All the way up here and all the way up there, but I just put arrows on just to kind of indicate that. That's what happens when we reflect in the y-axis. So we can see, well, what's this point here going to be? It's an intersection in the x-axis, and it's the same distance away from this intersection. So because that's the case, this here is going to be an intersection of -2, all because this was an intersection of +2. Okay, we're still crossing through the origin because that's on our mirror line, so it's going to stay. Okay, let's say this point here, I'll do this in orange, this point here was, let's say, let's just do the y value for the minute. Let's say it's y is, I don't know, let's say the y value is 3. Okay, might not be, just an example, but let's say it is, okay? So here is 3. Then what's the y value going to be over here? It's going to be exactly the same because we can just sort of work along that line. The y value will still be 3, but the x value will be the negative x value that it was here, just like we saw in the roots, okay? So let's have a look at the notation for that. The graph of something is a reflection of the original graph in the y-axis. To denote denote a reflection in the y-axis, we use this notation. Y is equal to f of minus x. Okay. I always remember it, the negative is with the x here, so because it's with the x, we do a reflection in the y-axis. Okay, we'll look at examples in a minute, but first of all, let's have a look at a reflection in the x-axis. So again, the same function, just an example function here, x squared minus 2x, a reflection in the x-axis. This time, it's this axis here, okay? So we're kind of treating that like the mirror, and we're going to do a reflection that way. It's going to look something like this. that will be our reflection, okay? And again, it continues down here. It doesn't stop, but we're just taking a section of the graph, okay? So this is our intersection. Here we've got an intersection on the x-axis, there we've got an intersection again because those are our roots that are on the x-axis there, on our mirror line if you like, so it's not going to change. But we can see our turning point goes from there and it kind of flips up to there. Okay, we can see if we compare x values, this is an x value, and that is the same x value. It's the x value of 1, actually. The x values stay the same. The only thing that changes is the y values. The y values, let's just work out what that would be. It would be 1 squared minus another 1, so that's going to be minus 1. If I just extend the graph down a little bit, this is going to be the value of minus 1, so that's going to be the value of 1. Okay, so we can see that coordinate there is 1, 1, and that coordinate there is 1, minus 1. Hopefully I've got that right. But we can see when we do a reflection in the x-axis, all of our x values stay the same, but our y values just become the negative of what they were. Okay, our y value was minus 1, the negative of minus 1 is 1. Okay, so notation for that, quite similar to the other notation. Did I write it in red? I did. I'll write it in red again. Quite similar to the other notation, but this time the graph of y equals minus f of x is a reflection in the x-axis. Okay, so this time the minus was outside the function. Okay, let's have a look at a final example for this video. So on the same axes, we want to sketch the graph of y is f of x, y is f of minus x, and y is equal to minus f of x, where f of x is x times x plus 2. So what I'm going to do is I'm going to sketch my original graph first. There we can see we want to sketch f of x. F of x is x minus 2, so let's sketch that. First thing we're going to do is find the roots, so let's set it equal to 0. X times x plus 2 is 0, so that's x is 0 or minus 2. So those are the two roots. So we'll draw those on there, 0 and minus 2. Okay, those are my two roots. And we can see if we were to expand those brackets, we'd get x squared plus 2x, so it's a positive x squared graph. I'll draw it in grey so we can have some colour here. We can see it's going to look something like that. Okay, let's try and match those 2 points up as well as we can. There, and then cross through the roots. Might need to move it down a little bit. Okay, it's going to look something like that. So that is, and I'll write it on, y is equal to f of x. Okay, next I will do in red, y is f of minus x. Going back to what I just said, if we have a minus with the x here, that is a reflection in the y-axis. Okay, so minus x, we're going to reflect in the y-axis. So what I'm going to have is a graph, and I'll do it in red, that is reflected in the y-axis, so it's going to look something like that. And I'll try and get it quite similar to the other. I have to look something like that. Not going to look perfect, but as long as we get the correct sort of look to the graph, okay? Move that point up a little bit maybe, like that, sort that bit out, okay? And then what we can do is add this intersection point on, okay? Here it was a negative 2, we've reflected in the y-axis, so it's going to be the same distance to here, but it's just going to change sign. Here we're going to have the points, and it's going to be x, 2, 0. Maybe I should add 0 on there as well. Okay, that's what happens. Oops, let's just move that a little bit to be in line there. Okay, our turning points must be in line. So yes, on the eye that looks quite good. Alright, final question is, now can we sketch, and we'll do this in green, y is equal to minus f of x. So the minus is outside the function this time, minus f of x. that is this example here. That's a reflection in the x-axis. So it's kind of the opposite. That's how I remember it. The minus is not with the x this time, it's outside the function. So because it's not with the x, we'll reflect in the x. If it is with the x, the minus is with the x here, we will reflect with the y. So you kind of do the opposite to where the negative is. So let's take my pen, we'll do it in green, and a reflection in the x-axis looks like this. Does not have to be perfect, you just have to get the correct shaping. Cross through the same roots because we're reflecting with the in the x-axis, and it's going to look something like that. Okay, now maybe it might be a good idea to put my turning point on here. So this is my turning point. I can see we're going to be at, let me see if I can work this out, x minus 1 and y minus 1, I think. So my turning point up here will be the x is going to be the same, minus 1, the y is going to become 1, okay, because we were coming down by 1 here, so a negative y. So if we flip it in the x-axis, we're going to be at a positive y.